in a straight line motion or rectilinear motion, the motion of the object is always supposed to follow a line. The path is a straight line. And then to determine the position of the object, we consider one point on this line as the origin, and then we consider a positive direction on this line. Okay? For example, like the traditional x-axis, we consider 1 point origin, and again, we might consider to the right side positive, to the left side negative, and we can change it if we want. But the good thing about it is now instead of the position vector, which connects origin to the current location of the particle, instead of that, needed to be shown using a vector, right? Using magnitude and direction, we know the direction of this position vector is always parallel or on this line. Parallel to the line or on the line, doesn't matter. So all we need now to describe the position of the object is the distance of that particle to the origin, which we show with s, and the sign of s, right? Whether it's positive or negative. So we can change position vector from being a vector really to what? A scalar s with a sign. So that simplifies a lot, okay? And we know from physics that it's always easier to deal with the scalars than vectors. So that's the advantage. Now, before I get into other definitions, where in real life you see this type of motion, a straight line motion, where is it that the object is basically constrained to only move along a straight line? Yeah, probably one example will be the slider crank mechanism or a piston inside a cylinder, right? So if you know the engine of a car, you know that basically you have something like this, right? So this is the crankshaft that is rotating, and then here connected to the crankshaft I have a member, right? And then connected to the end of that member I have a piston that moves inside a cylinder, correct? So this is a piston, of course, and this conrod, of course, is not just a straight line. So if we want to do proper graphics, we have to draw a conrod, but here I'm just trying to make life simpler, but you can, of course, always use better graphics. I'm not the best at drawing it, but basically what you have for a conrod, if I want to make it very simple, is you have something like this. Okay? So if you look at the motion of this piston, it is only supposed to go up and down inside the cylinder. So this motion of the piston can be described as a rectilinear motion. Now, displacement, of course, is defined as the change in position. So if initially you are at position S and then next you are at position S prime, then delta S is the difference between S prime and S. And of course, this displacement can also be considered a scalar, but with a sign. So if delta S is positive in this case, means what? And assuming that the positive direction is to the right. Okay, so if this is the axis and this is the positive direction and that is the origin, and this is the particle and this is distance S. So when delta S is positive, it means what? You are moving to right, and when it's negative, it means you are moving to left. Okay, so that's the meaning of displacement, of course. Now, velocity similarly can be defined as rate of change of position. And since the velocity is always tangent to the path and the path is a line, so velocity is also always on this line. Okay, the line of action for velocity is the same as this line. So instead of velocity being considered a vector, I can just consider it to be what? Again, a scalar with a sign, right? Positive velocity, negative, or zero, correct? So similarly, as I said, we define instantaneous velocity to be what? ds over dt, and average velocity to be what? Delta s over delta t. And when instantaneous velocity is positive, it means, again, you're moving to the positive direction. In this case, it means to the right. Not always it means to the right. In this case, we consider the positive direction on the right side. So for this case, positive velocity means moving to right. Negative velocity, again, means moving to left. And zero means what? Means temporarily you are what? Stationary or not moving. Right? You are at a temporarily stop. So clear meaning. Now, what about acceleration? The same thing, it's rate of change of velocity. And again, acceleration falls on this line too. So I can again consider acceleration to be a scalar with a sign, positive, negative, or zero. Now, what's the meaning of positive, negative, or zero acceleration? So let's take a look at this, because this is one of the things that my students sometimes are confused about. So these were what? Instantaneous and average velocity, and the meaning of that. Now, instantaneous acceleration is defined as dv over dt, and average acceleration is defined as what? Delta v over delta t. Now, what's the meaning when a is positive? What's the meaning when a is negative? What's the meaning when a is zero? Okay. So when a is positive, does it mean the object is moving to the right? Not necessarily. Positive a means what? Means your velocities are increasing. And increasing does not necessarily mean in magnitude. It means they are getting more toward positive numbers. What do I mean? So if you initially had a positive velocity, consider a car. Right? Consider a car. If you are moving forward at 10 miles an hour, and then you push on the accelerator, then you're going to get positive acceleration. And so the velocity of 10 now becomes 12, 15, 20, and keeps increasing. Right? So this is a positive acceleration. But is there any other scenario? Yes. What if you were moving backwards, right? It was in rear gear and you were moving backward, but then all of a sudden, what do you think? You were moving backward, now you nailed the brake. What happens? What kind of acceleration do you have if you're moving backwards, in this case to the left, and then nail the brake? Does it give you positive acceleration or negative? And note that you're moving backwards. So you might say, well, the acceleration is negative. Well, not necessarily. Because, let's say in the beginning, you're moving backwards at 10 miles an hour. But that 10, since it's backwards, and it has sign, so it's negative 10. Now, when you nail the brake, what happens? From negative 10, you go to negative 5, negative 2, and then 0, you stop, right? So what happens when you go from negative 5 to negative 2? Is your change in velocity positive? This delta v or dv, is that positive? Or because delta t, change in time, is always positive. So when you go backward, but slowing down, the delta v is still positive, right? Because you are subtracting what from what? The new velocity, which is negative 2, minus the old velocity, which is negative 5. So you end up with positive 3, right? So it is still positive acceleration. So what is positive acceleration in this case? It means basically accelerating while moving forward or in the positive direction, or decelerating while moving backwards. Okay, so if you're going backwards and you nail the brake, that is also positive acceleration. So you see, positive acceleration does not show which direction you are moving. You can move in either direction. It shows how the values of the velocities are changing. The same thing for negative acceleration. What does it mean for driving a car? You're moving forward, but all of a sudden you nail the brake. What happens? You go from 10 to 5 to 2 to 0. So if you subtract, you're subtracting now 2 minus 5, which is negative 3. So nailing the brake when you're moving forward, that is negative acceleration, correct? So decelerating, stopping. Let me use a different color. So decelerating while moving forward is a negative acceleration. And is that the only case? No. If you are going backwards and then you push on the gas, on the accelerator, what happens? You go from -2 to now what? -5, -10, -20, because the speed, the magnitude of velocity is increasing, but you are going backwards. So now you are subtracting -20 minus -10, which is still -10. Okay? So when you're moving backward, if you accelerate, that is also negative acceleration. So again, you see, it doesn't say anything about the direction of motion. What about zero acceleration? What does it mean? When you have zero acceleration, are you moving? You see here, when your velocity is 0, you're not moving. What about zero acceleration? If you have zero acceleration, are you moving? Yes, you can. When you're just cruising, whether backward or forward, doesn't matter, and the magnitude of your speed and the direction of your velocity does not change, you have zero acceleration means the velocity does not change. And when we say velocity does not change, means both what? Both magnitude and direction. None of that should change. Otherwise, you do have acceleration. So the meaning of it is magnitude and direction of velocity is not changing. But the velocity does not need to be 0, okay? It can be a constant number, whether positive or negative, okay? And why did I emphasize this direction? Because it is really important. So one of the examples that you probably see a lot is, and we're going to see it in this course, is circular motion. If you are going around a traffic circle at a constant velocity, okay? So let's say you're going with a constant velocity of 10 miles an hour around a circle. Okay, you're rotating the traffic circle. Do you have acceleration or you don't? You might say, well, this guy is constant, right? The magnitude of velocity is 10, the speed is constant. So I do not have acceleration. Yes, you do, right? Why? Because here, you know velocity is tangent to the path. So here, your velocity, although magnitude 10 is in this direction, but when you come here, The magnitude is still 10, but it is tangent to the path, so it is in a different direction. And when you come here, again, it is in a different direction. So this circular motion, although constant speed, does have an acceleration. What is it? You probably heard of it. It is an acceleration called centripetal acceleration, which we're going to study in this course. Okay, so in this motion, A is not equal to 0. Okay, so hopefully now we understood the meaning of displacement, velocity, acceleration, and everything in rectilinear motion. Good. Now let's get to the differential relations between A, V, and S, which are extremely important, and look at one example together. And then we'll look at more formulas, and then we're going to leave some of these problems for inside our classroom. Okay, so we're not going to solve all of them. We're going to solve some. So probably I would solve one example here, and then one example from the next one. And then the other examples we're going to leave for inside our classroom, because that's where we go over topics that you might have questions, and we solve more examples. So differential relations or equations between velocity, acceleration, and position. Well, we just learned the relation between V and S. V is dV over ds. V is ds over dt. So what does it mean? Graphically. What does derivative means graphically, right? From what you learned in calc, derivative, first derivative, what's the meaning of first derivative in a graph? What's the meaning of second derivative in a graph? And what's the meaning of integral in a graph? Okay, so these are the stuff that you should have seen in your calc course, but just I am going to emphasize those. So if you have a function like f versus or y versus x, and this is a test point, so at this point x 1, let's say, what is the first derivative? Well, we know the first derivative means what? The tangent line, the slope of the tangent line. So if I draw a tangent line to this curve, the slope of it, which is also the tangent of the incident angle alpha, right? So dy over dx at point x equal x1 is equal to what? Tangent of alpha is the slope of the tangent line. That is what? That is the first derivative. We know that. What is the meaning of second derivative? So what's the meaning of the second derivative of y d squared y over dx squared at point x equal x1? What's the meaning of that? Positive, negative, 0. It's the meaning is what? If you learn probably, that is the curvature. Okay? So when this guy is positive at any point, it means it is curved upward, right? So this is positive curvature. This is negative curvature at the point, correct? And 0 curvature means the slope does not change, okay? A point like this probably. Right, or it doesn't have to be always necessarily flat at that point. As long as the slope on the left and right does not change, we can get 0 slope at that point, called an inflection point. Okay, so these are the meanings of, or not A necessarily, I have to clear that. Let's not call it A, let's call it the double prime. Right, y double prime. And what is the integral? We know it's the area under the curve. So if I say the integral of this function, if I call this function y equals f of x, and if I say what is the integral of f of x dx, x from x naught to x1, and x naught is, let's say, a point here. This is, from your calculus, is what? The area under the curve, right? Okay, so second derivative is curvature, and integral, if I can make it smaller, integral is area under the curve. So these are really important from your calc. Now, when we say ds over dt means what? Means if I have a graph of position versus time, the slope of the tangent line at any point is what? Instantaneous velocity. What was the average velocity? What was displacement? I mentioned all of them here for you also at the end of the lecture as a reminder, so you can look at them. Let's go over them here. At the end, these are material for further study. So again, if I have a plot of s versus t, at any time point, the slope of the tangent line is going to be what? The instantaneous velocity, right? Good. What about the average velocity? If somebody says, what is the average velocity, what would you do? So instead of that, I have a curve like this. So this is s versus t, and it's an arbitrary graph. And this is point t1 and s1. And this is point t2 and s2. Okay, so if I say, and let's call this point also t3. If I say what is velocity at point t3, that is the slope of the tangent line, right, at that point. So it's not a big deal. But if I say what is the average velocity for t between t1 and t2, then it is what? It is delta s over delta t for this range, which is going to be s2 minus s1 divided by t2 minus t1, which, if you remember, that's the slope of a line that connects these 2 points together. So slope of the red line is average velocity. Okay, so this is how we get average and instantaneous velocity from an ST graph. And what is this quantity here? This is your displacement. Okay, so easy. Now, a similar thing we can apply to get acceleration from a VT graph. So if I have a VT graph exactly similar to this case, so I have a VT graph, then very similarly, if I have point T1, T2, and T3 maybe, and then V1, V2, and V3, if I say what is the acceleration at time T2, instantaneous acceleration, well, it is dv over dt at that point, which is the slope of the tangent line, which is this guy, right? You draw a tangent line. The slope of that, which in this case clearly positive, that is the acceleration. Now, sometimes I might say, what is the average acceleration for t between t1 and t3. Well, that is delta v over delta t for this range, which is going to be the end velocity v3 minus beginning velocity v1 divided by beginning time t3 minus end time t3 minus beginning time t1. Okay, so you have to connect this point to this point. In this case, still positive, but you see the slopes are quite different, right? The black line has a larger slope. So this is getting, if you want to go from S to V, you look at the tangent of the slope. And if you want to go from V to A, again, you're going to look at what? Tangent of the slope, because you are taking one-time derivative. Now, can I directly go from S to A? Yes, but you need to take what? Second derivative, right? So you need to go from, let's see if I can draw here. You need to go like this, and you need to do a second derivative, which is curvature. So you can do that. If I ask you at this point, let's say t1, what is the sign of acceleration? We cannot easily find the magnitude, but what is the sign of acceleration at t1 for this black graph? What is it? Well, you just look at the curvature. You see the curvature is down, so it is what? Negative. But for t3, the curvature is upward, so the acceleration for point t3 is what? Positive. So you can at least infer the sign of acceleration in ST graph, if not the magnitude directly. Okay, so this is the relation between SV and A derivatives. Now, of course, if you want to go backwards, you have to do the opposite of derivative, which is what? It's integral, right? So I have a t graph, right? I have a graph of acceleration versus time. And let's say this is time t1, this is time t2, and this is a1, and this is a2. Now, if I ask you, what is the velocity of the object at point t2 from this graph? Can you find it? If I exactly tell you what kind of function is this, so I exactly know a versus time, I know this function. Can you give me the magnitude of the velocity at point t2? No. You need one more thing to do that. If you want velocity at any time point, not only you need to know a as a function of time, you also need to know the velocity of the particle at another time point. So let's say at t equal t1, I know how much the velocity is. So I know this number. Okay, it's given to me. Let's say that's when the motion starts, or I could sense the acceleration at the velocity at that point or something. So I need two pieces of information. Not only A, I need to know versus time, I need to know V at another time point. Then I can find V at any other point. How? I say, well, A is what? dV over dt. I do a cross multiplication. I would get dV is A times dt, or if you want to be more accurate, I would write it as A of t, because that's a function of time in general, not always A is constant. Now what I do, I integrate both sides of this guy. And then I apply lower and upper conditions, right? Limits of the integral. So I want this integral to be taken from time t1 to t2, and this integral over v to be taken from velocity. Let's say this one is given as v1, okay? So this number that is given to us, we call it v1. It is given. So it is from v1, correct? This is from v1 to v2. v1 is given, but this v2 is not given, okay? So we do this. Now what? What is the integral of dv? It's delta v, or v, right? V, so it is going to be what? v2 minus v1, and this is still going to stay the same. T from a of t dt from t1 to t2, correct? Yes? And then if I want, I can take this negative v1 to the other side, so I can write it like this, if you don't mind. I would write it like this. Okay, and this guy here is how I find velocity at one point based on the integral of acceleration from between the 2 points and the velocity at the beginning. And what's the meaning of this? We know, based on what we just said, integral is what? Area under the curve. So if I can calculate this area between t1 and t2 and call it a, this quantity, whole thing, is what? A. So if I calculate that and add it to v1, I get what? v2. Okay, so whenever we want to go back from a to v, how do we go back? By doing integral. And similarly, and of course we need to know what? Some initial condition. And similarly, when I want to go back from v to s, again, I need to do what? Integral. So similarly, I can easily show you that since v of t is ds over dt, if I cross multiply, and then I integrate, this is from t1 to t2, and this is from s1 to s2, and solve for it, you're going to see that s2 is going to be s1 plus integral from t1 to t2 of v of t dt. So if v is given to me as a function of time and some initial position, I can find another position, okay, at any other point, okay? So that's what you can see in these graphs, right? Integral versus derivative. And now let's look at an example together. Let's look at an example, and then we come back later to this time-independent equation and more examples. But what I want to work with you is working on one of these, one example related to this integral and position velocity graphs, and then we go back to the rest of it. So let's start. So this is the example that I have for you. So if I have the graph of velocity versus time, I had a radar, a LiDAR, a sensor that could measure the speed of a person running. And this is the graph that I got. Oh, let's use the straight lines. See if I can get this to work. And then maybe Okay, so it's a bunch of straight lines. And let's say this time point here is 2, this time point here is 3, this time point here is 4, and this time point here is 5 seconds. The unit of velocity is meters per second, and let's say the values that I have recorded are like 10, and this one is negative, let's say 3. Okay, so now my question is, if I tell you at the beginning of the time, s at time 0 was 0, so I started at origin. Okay, so I give you this piece of information. Now I say, first of all, let's make it smaller. What is the velocity of the object, instantaneous, at time t equal 2.5 seconds? What is that? Then I say, what is the average velocity between 2 seconds and 4 seconds? Then I say, what is the position at time equal 3? And then I say, what is the acceleration at, let's say, t equal the instantaneous acceleration at time t equal doesn't matter, any number, 3.5 seconds. And then what is the average acceleration between 3 seconds and 5 seconds? Okay, so I have given you some initial piece of info, which is s at time 0, and then I'm asking for a ton of info from you. So how do we determine these? Well, since it's v versus t, if we want to determine velocity, instantaneous velocity at any point, I directly go read it off the chart. Okay, so 2.5 is here. And this is a straight line, horizontal line. So you see, for all points between 2 and 3, the velocity is constant at what? At 10. So this number is directly what? 10 meters per second. So instantaneous velocity I directly read. Not a big deal. Now, average velocity, on the other hand, is not as easy as you just read it off the chart. No. Because this guy here is basically delta s over delta t. The distance traveled over time, or the displacement, I'm sorry, the displacement over time. Now the question is, I can see time is between 2 to 4, so it's 2 seconds, but what is displacement between 2 to 4? I cannot see it immediately from the graph, but if I go back to the previous slide, look at this guy. This is what I have. If I take S1 back here, what is this quantity? That's delta S. So delta S, the displacement, is what? Area under the curve of velocity between the 2 points, right? So if I go back here, between time 2 and time 4, which is here to here, I need to know the area under the curve. So I need to find this area. if I find the area of the hatched shaded area, if I find the shaded part, then if I divide that by delta t, that's the average velocity. So how do I find that area? Well, not a big deal. It's a trapezoid and what? A triangle. Now, pay attention that the trapezoid is above the t-axis, so the area here is positive, while for triangle it's below, it's negative. So when I want to calculate that, I have to pay attention. So it's going to be the area of the trapezoid minus the area of the triangle divided by the time difference, which is 4 minus 2. Now, what is the area of the trapezoid? You see, one side of it is from 2 to some point that I don't know. The other side of it is 2 to 3, so it's 1. The other base I don't know. The height is 10 units. So first thing is there any way I can find this point? I need to know the location of that point, okay? If I don't know the location of that point, there is almost nothing I can do. So how can I find it? I need to know when, some other part of this problem. Let me add one more thing. When is it that the velocity goes down to 0? At what time point the object is at a temporarily stop, which is basically this point here. Where is that? Well, to know that, I have to know the equation of this blue line here. So first, let's find out the equation of the line as t goes from what? 3 to 4, right? Between 3 to 4. We have to know the equation of this line. So if I want to write v as a function of time, as a multi-criteria function, v versus time, how can I write it? So between 0 to 2, that's quite easy. What is that? It's a straight line from origin with the positive slope. What is the slope of it? It's 10 units vertical divided by 2 units horizontal, so it's 10 divided by 2, so it's what? 5, positive 5. What about between 2 to 3? You see, it's at a constant number, positive 10, right? Because, oh, I'm sorry, positive 5 times t. Not positive 5. Positive 5 times t, because it's a line and it's changing versus time. So 5 times t. Between 2 to 3 is constant 10. Now what about between 3 to 4? So if I want to write it between 3 to 4, now what? And then between 4 to 5. So between 3 to 4, it's a line with negative slope and it has a fixed point. Either we can use 3 and 10 or we can use 4 and negative 3. You know the equation of a line, if you know 2 points of it, the equation of a line in general is what? Y minus y2 is equal to y2 minus y1 divided by x2 minus x1, which is the slope, times x minus x1, right? This is what you learn in your high school for equation of a line given 2 points. Now in this case, instead of these guys, what do I have? In this case, it is v minus v1 or v2. We can use any of the 2 points, it does not matter. V minus v2 is v2 minus v1 divided by t2 minus t1, the slope, times t minus t2. Okay? Now, I would rather use t minus t1 and v minus v1 because we want positive delta t. So if you don't mind, I use 1 instead of 2. It does not change anything. So what are these values? Now, if you look, t1 is 2, t2 is 3, v1 is 10, and v2 is negative 3. So it is going to be negative 3 minus 10. This is 4 and 3. 3 and 10. So if you simplify it, it is going to be v equals, so that's 1, that is negative 13, times that positive 39 plus 10 is 49. So that is the equation of that line, negative 13t plus 49. Now, is that correct? We just plug in the number back. If you plug in 3 in this, it is going to give me 10. If I plug in 4, it is going to be negative 3. So that's right, negative 13t plus 49. So negative 13t plus 49. That's the equation of the third line segment. And then if I want, I can find the last line segment as well. It does not hurt. I can do that. So it's between 0.4 and negative 3 and what? 5 and 0. So for the second line segment, if I do it, v minus v1 again is v2 minus v1 divided by t2 minus t1 times t minus t1. In this case, v1 is negative 3, v2 is 0, and t1 is 4, and t2 is 5. So if you simplify this case, the slope is going to be positive 3, so it's going to be 3 times t. That is negative 12 minus negative 3, negative 15. Now if I plug in 5, it gives me 0. If I plug in 4, it's negative 3, which is right. So 3t minus 15. So this is the equation of the velocity versus time. If I convert that graph into math, this red one is what I would get. Okay? Now, let's go back. Sorry. Let me just draw a line between them so that they are not too badly messed up. Okay, so now the big question was, what is the point at which the velocity was 0? So I need to know the location of that point. And that's where I need this function here for the third line segment. I need this guy to be equal to what? 0, right? So negative 13t plus 49. This guy has to be equal to 0, and if you solve for it, you see that t at that point is 49 divided by 13, right? I can just write it as a fraction. So at that time point, and clearly this number is between 3 to 4. At that point, the velocity hits the 0. So now, if I want to calculate the area of the trapezoid, one base of it is 1, the other base is between 49 divided by 13 and 2, and then the height is 10. So it is going to be 10 times 1 plus 49 divided by 13 minus 2, that's the other base, the whole thing divided by 2, and then the area of the triangle is what? It's the base, which is 4 minus that 49 over 13 times the height, which is 3, and then divided by 2. Okay, so this is going to be the average velocity between those points, and I am going to use MATLAB and calculate that for you, although we probably can do it without MATLAB as well, but let's just get a proper decimal. and round it to 2 decimals as I said in the very first video. And then we move forward and we calculate the rest of it. I just want to make sure that you can do this task without any problem. Okay, so 49 divided by 13. You need to wait a few more seconds. This is the new MATLAB I installed, so it takes a few seconds, but should be done fast. Okay, so this number was 3.77. And now, if I calculate this guy, this is gonna be 1.77 plus 1, 2.77. So this is gonna be 5 times 2.77 minus, this is gonna be 0.23. So 0.23 times 1.5, which is 3/2. Then the whole thing divided by 2, right? So 5 times 2.77 minus 0.23 times 1.5. Then the answer divided by 2, which is 6.75. meters per second. Don't forget the units, please. Always write the units. So you see clearly the average velocity is different than instantaneous velocity. An average velocity from a VT graph, although it's a VT graph, but average velocity takes a lot more work than instantaneous one because you cannot rate it directly off the chart. Now, somebody might say, what is the position of the object at 3 seconds? Well, to do that, we use this formula we just learned. That position at any point, we use this formula. Position at any point is the position at some initial point plus the area under the curve between the 2 points. So if I want this, this is equal to s at time 0 plus the integral between 0 to 3 of v of t dt. Now s at time 0 is 0, it's given. So the integral of v dt between 0 to 3 is simply what? Yes, area under the curve of vt between 0 to 3. So it's this green area. And it is a simple trapezoid. One base is 3, the other one is 1, the height is 10 and divided by 2, okay? So this is going to be 0 plus 10 times 3 plus 1 divided by 2, which is going to be 20 meters. So if I started at origin at time 0, now after 3 seconds, I'm 20 meters away in the positive direction on the right side of the origin. Now, what is the instantaneous acceleration at 3.5 seconds? So 3.5 is on this line, right? It's between 3 to 4. And we know that instantaneous acceleration is what in a VT graph? Yes, a slope of the tangent line. In other words, what's the slope of the tangent line here? Since this graph itself is a line, tangent to it falls on the line itself. So in other words, what's the slope of this line? And clearly you can see the slope of this line is what? Negative 13. We already calculated it, right? So it's the slope of the line connecting point 3 and 10 to point 4 and negative 3. So all I can do is just to subtract. I can say it is the velocity at 4, which is negative 3, minus the velocity at 3, which is 10, divided by what? 4 minus 3, which we calculated to be negative 13, and the unit is meters per second square. Okay? Now, in this case, if somebody says, what is the average acceleration between 3 to 4? Average acceleration is what? The slope of the connecting line. So if you connect points of 3 to point T4, that's the same as what? This line. So in this case, because the VT graph is a line, the instantaneous acceleration and the average acceleration at any point are the same number. But just because VT is a line. If it's an arbitrary curve, that's not the case. Or if the connecting point between the connecting line between the 2 points is not on the graph, like the bottom case. So between 3 to 5, if I connect point 3 to point 5 with a line, the slope of this line, this line itself, is not on the curve. So I would get a slope that clearly is negative, but it's not going to be 13, it's not going to be 3, none of them. So how do I find it? I calculate the velocity at t equal 5 minus the velocity at t equal 3 and divided by 5 minus 3, which is going to be 0 minus 10 divided by 5 minus 3, which is going to be negative 5 meters per second squared. Clearly it is negative, but as I said, it's neither negative 13 nor 3. Okay, it's none of those numbers. So hopefully this example basically showed you how to do these types of graphs and solve these types of problems. Now, somebody might say, could you also construct the AT graph in this case for me? And the answer is yes, I can. So let me take that to another page just as an extra bonus for you so that you practice enough on this topic. Okay. Control C, hopefully it allows me to paste here. Control V, there we go. Okay. So now if somebody tells me, what is the AT graph going to look like? Well, I can tell. So if I want to do the AT graph, all I need at any point is the slope of the line, because this is a simple case. Between any two time points, it's always a line, so the slope does not change. So I can just take a time derivative from this guy and say that a of t is going to be the slope, which is 5 between 0 to 2. Between 2 to 3, it's a horizontal line, it's a constant number, the slope is 0. Then between 3 to 4, the slope is negative 13. And finally, between 4 to 5 is positive 3. Okay, so if I want to plot it, I'm going to go like 5, then go 0, then go negative 13, and then go positive 3. Okay, so this is 3, this is negative 13, this is 0, this is 5. So there's going to be piecewise function. It's not going to be a continuous function anymore. Okay, so acceleration suddenly changes from this at this point or at this point and this point. And this is going to be a jerky type of motion. By the way, the word jerk, it's not a bad word in dynamics. Jerk is another thing probably you have not heard in your physics. Jerk, J, is the time derivative of acceleration. Okay, dA over dt. So if you take another time derivative from acceleration, that quantity is called jerk. And so if acceleration at any point is discontinuous, like this point, or this point, this guy is going to be practically infinite. Okay, and that means a huge force is needed to make the system behave like that. Okay, and you're going to feel it. So just for your own knowledge. So I guess I have covered these topics. Now, let me talk about the time-independent equation. So time-independent equation is where you eliminate t between a, v, and s. So you see, when I go from s to v to a, or vice versa, I'm always dealing with t, with time. Is there any way to get rid of the time? The answer is yes, you can, and that gives us a very useful formula that you can see here called time-independent equation, which many of the times that we are not interested in time, only in position, velocity, and acceleration, it can give us the answer much, much faster. So let me just very fast go through that. Since A is dv over dt, here I apply what we call the chain rule. And please, if you don't know chain rule or you forgot it, go back to your calc and study that a lot in detail. In this course, we need to use chain rule all the time. And that has been a source of credit loss in my classes always in the past, that my students could not carry a proper chain rule. So what we do here, instead of taking derivative with respect to time, I take derivative of velocity with respect to position, and then take derivative of position with respect to time. Okay, it's kind of like these two dS's would cancel out and you get dv over dt back. So this is called chain rule. Okay, and we use this guy a lot again in this course. I will emphasize it more. So now this guy we keep. ds over dt based on definition is what? V itself. So the result is A is V times dv over ds. And this relation, which there is no t in it, is called the time-independent equation. Okay, very important differential equation between them. Or you can cross-multiply and get A times ds to be what? V times dv, and then integrate both sides. That's another way to look at it. This is from S1 to S2, and this is from V1 to V2. And this right-hand side integral is integral of v dv, so it is going to be v2 squared over 2 minus v1 squared over 2. So that's another way to look at time-independent equation, either the one in blue in differential form or the one in green in an integral form. Okay, so this time-independent equation is going to give us the answers many times that, all the times mostly, that time is not a matter of concern. It is really important, and we're going to use this in this course. Okay, so this example 13.3 I will keep for the class because we are going to maneuver around it and solve more problems in class. If I do everything here in the lecture, then there will be nothing left for the class. So we'll keep that for classroom. Now, I would also like to do the same thing for this example. So I'm gonna look at these equations, but I'm not gonna do this example here. I'm gonna do this example inside the class, and this is one of the interesting examples that is not in the textbook, but it is really important about driving, basically. So these two in the red box are specific cases of rectilinear motion. Two special cases. One where the velocity of the object is constant. We call it a uniform motion. If the velocity is constant, equal to vc, then, of course, since velocity is constant, there is no acceleration, it's zero. And if you integrate a constant number in this formula, if you integrate the constant comes out of the integral, and integral of dt is delta t. So delta s is going to be that constant v times delta t, and delta s is s minus initial s. So if you bring the initial s to the right hand side, you're going to get this simple formula for the position. Okay? So this is called a uniform motion, and graph-wise, so this is v versus t, this is a versus t, this is s versus t. So graph-wise, it means the velocity does not change. So it's a constant number, it's a horizontal line versus t, and either this constant number is what? Positive, or this constant number is what? Negative. Let me use a different color for this case. So it's constant, whether positive or negative, it does not change. So this is the uniform motion. So pay attention that the velocity is constant, not just the speed. Not only the magnitude of velocity has to be constant, the direction should not change as well. So circular motion that I mentioned in the past, it is not a uniform motion. Then acceleration is always zero regardless, because velocity is constant, so acceleration is zero. And the position is a linear function of time. S is s naught plus v times t. So it can be either like this, or it can be like this. Okay, so this is for the negative case. This is for the positive case. And this constant number at the beginning is what? Initial position s naught. Okay, so this is the uniform motion. Where in real life you would see uniform motion? Well, it's not so common, okay, because you have to keep the acceleration zero, which means sum of the forces is zero. So you have to always keep the object in balance, at equilibrium. So it's basically not easy, but let's say if an object, a space shuttle, is in the space moving and far away from the effect of gravity of any planet, okay? So it's in an almost empty space in the universe. There is no force acting on it and no drag, nothing, because there is no air. It can keep moving at a constant velocity unless you turn on some thrust or something. Okay, so you need to counteract the other effects and cancel them. Or let's say if you are cruising your car in a road that is a straight line, that can be considered a uniform motion. Okay, so there is only one equation for it, s equal s naught plus v times t. Now the other type of motion, which is more common, is when acceleration is constant. Whether positive or negative, the acceleration is constant. Constant acceleration means sum of the forces is equal to a constant number. So sum of the forces is not zero, but it's constant, okay? A circular motion where you keep the speed constant is a kind of constant acceleration motion. Now, if we call that constant acceleration AC, if I integrate this from this equation, A equal dv over dt, if I integrate that, I see that velocity is going to be a linear function of time, right? So velocity is going to be initial velocity plus acceleration times time. And if I consider velocity to be what? Because now v is a linear function of time. If I integrate it here one more time to get position, what happens? Your position is going to be a quadratic function of time. Is initial position plus initial velocity times plus half acceleration t squared. And if I eliminate the time between v, a, and s, get this time independent equation, and integrate the left side, since a is constant, it comes out. So you're going to get a times delta s is equal v2 squared over 2 minus v1 squared over 2. And if you cross multiply, you're going to get this equation. That v squared is v0 squared plus 2a times delta s. Okay? So here we learned that s is s0 plus vc times t. Now, if I look at constant acceleration motion with you, so this is t, this is s, this is v, this is t, this is a, and t. Here a is constant, so it's either a positive constant number or it is a negative constant number. Doesn't matter, it should be constant. Then you can clearly see that v is going to be a linear function of time. So if a is positive, v will keep getting more toward positive numbers. So it is going to be like this. Or it is going to go like this. So v is going to be a c constant times t plus initial velocity v0, which is this point here, v0. Okay? What about s? S is going to be a quadratic function of time. So s was s0 plus v0 times t plus 1/2 a times t squared. Now it can have different shapes. So let's say this is point s0. This is where the motion starts. Now here the shape of this curve depends on the sign of a and the sign of v0. You have two pieces of information that would form the shape of this curve. So if it goes something like this, what do you think? This is a quadratic function, right? This is a parabola. What case do you have here? First of all, since the curvature at any point is positive, this is the case where AC is positive. But what about V0? V0, V is the slope of the tangent line in ST graph. So V0 is the slope of the initial tangent line. So if you draw a tangent line here, the slope of this tangent line, which in this case clearly negative, it means V0 in this case is what? Negative. So it looks like this. Now it could be something like that, for example. What about this case? What about this blue parabola? Clearly curvature is negative, so AC is negative. But if you look at the initial slope is what? Positive. Okay, so you can have different shapes. Sometimes both of them are positive or both of them are negative. If that's the case, then you probably do not have a min or max point. Okay, it just keeps directly going up or directly going down. So you're going to get curves like this, basically, with no max or no min. Or sometimes it looks like this. What about this case? In this black case here, the acceleration is negative, the curvature is downward, but if you look at the initial slope is what? It's 0, because you start horizontally in the beginning. So you can get different types of shapes. And when would you have a max or a mean in ST graph? When the sign of V0 and AC are different. When the sign of V0 and AC is different, then you would get a max or a min. Okay, so that is important. And finally, we had the time independent equation, which says V squared minus V0 squared is equal to 2AC times delta S. So you see, it relates A, S, and V together, and V0 without the need for time. So this is an extremely important equation that we use a lot in this course. Again, I'm going to go over this example later, okay? Because we want to solve some stuff in classroom. Now, so far what we have seen is when A versus time is given, or V or S versus time is given. So we know everything as they change versus time. For example, let's say A is given to us, like in this graph. Actually here. So A is given, and then what you want to do is find V versus T or S versus T, then you integrate them once and then twice, right? So that's what we have done. But sometimes your acceleration of the particle is not a function of time. It's a function of position or velocity. In those cases, a simple integral versus time is not going to do anything. Let's look at this example 3.4, and this is where you have to solve differential equations directly. So when an airplane is landing, because it is really fast, to shorten the distance it needs to stop or reduce its speed, they also basically apply a parachute. They open it up, and that will add some extra drag, which brings the velocity down. But the acceleration coming from the parachute, the drag force or the drag deceleration, is not a function of velocity, it's a function of velocity squared, as you have seen or you would see in your fluid dynamics. Now, if it lands with a velocity of 80 meters per second and deploys the parachute right away, and the formula for the drag, the acceleration due to the parachute is this formula, A equal negative 4,000 V squared. I want to know how much time it takes for it to go down from 80 to 10 meters per second, and during this reduction in speed, how much has this airplane moved on the runway. So we're going to look at this problem. The other case we're going to look at is one of the end of chapter problems where acceleration is a function of position, and that's where we connect mass to a spring and the force of the spring, and so the acceleration coming from it is a function of position. A is negative 4 times S. In that case, we also need to solve a differential equation. So what I would do, I go over this problem with you right now, and then I would leave this other problem for our classroom. So this problem says that initial v is 80, the final v is 10 meters per second. I want to know how much time it took for it to happen and how much the object has moved during this time if acceleration is negative 0.004 v squared. Okay, so that's what the problem is asking, and that's what I said, writing what is known, what is unknown. So always write in a way that everybody can read. Okay, so clearly here I don't see any time directly, but indirectly, yes, it is in A, right? What's the definition of A? As you know, A is what? dv over dt is now equal to 0.004 v squared. Now if I say, what is this guy here? What kind of equation is this? Is it an algebraic equation or a differential equation? And you would probably tell me, yes, it is a differential equation. If I ask you, is it linear or nonlinear? What would you say? Yeah, you would say it is nonlinear because I have the function v squared. If I say what's the order, you would say it's first order because I only have first derivative of v. So it's a first order nonlinear ODE. And one of the most common techniques that you have probably learned in your DFQ course, when you want to solve this, you use the method called separation of variables. So you bring all the v's, or all the dependent variables and their derivatives on one side, and the time or the independent variable on the other side. So this is, I can write it this number divided by 1, right? And now what I want to do, I change the position of this term here with this term, if you don't mind. Or maybe not the negative 0.04, just the negative v squared of it. That and dt, I would exchange their position. Right? I can do that when two ratios are equal. So you're going to get dv over negative v squared is equal to 0.004 dt. Yes? This is called separation of variable. Here is all v, here is all t. Now, when that's happening, I can integrate both sides. This goes from initial time 0 to the final time t that I don't know. This goes from initial velocity 80 to the final velocity 10 that I do know. Okay, and now if I integrate, what happens? What is integral of negative 1 over v squared? Yes, that's 1 over positive v, calculated at 10 and 80 and subtracted. And this is going to be 0.004 t. Right? So if you continue, it is going to be 1 over 10 minus 1 over 80. It's going to be equal to 0.004 t. Therefore, t, or delta t in this case, because initial time is 0, you can find that it is going to take, 1 second, we have it, 21.9. So it takes 21.9 seconds for the airplane to go from 80 to 10 meters per second with the help of parachute. Okay, so this method, again, we call it separation of variables. So this is the first part of this problem. So I got this one. What about the displacement? So if I want displacement, what can I do? So one way, if I want displacement, is, we know if I want displacement, I can go back to velocity and integrate it versus time, right? If you go back here, Displacement is integral of velocity versus time, but I need to know v as a function of time, which in this case I don't. V versus time is not given. I only have v at 2 time points, not between these two. If I knew, I could do it. Now the question is, can I find it? Yes, and I'll show you. But the simpler way is, can I just get rid of time at all and just focus on V, A, and S and get rid of time? Well, probably if I use what? The time independent equation, which is this guy here. A equals V dV over ds. If I use this one, or the cross multiplication version of it, this one, then probably I can easily solve for delta S without the need to ever find time. All I need to do here is to replace A. And for A, I replace it from the equation given, which is negative 0.004 v squared. And what I can do is I can get rid of one v term from both sides. And then I bring all the v's on one side and keep the s on the other side. So if I do that, I would get what? I would get negative 0.004 ds is equal to dv over v. Okay, or in other words, I simplify both sides by v squared. And now all I need to do is to integrate both sides. Yes? This goes from initial velocity, magnitude velocity of 80 to 10. And this goes from initial position that I don't know to final position s or delta s. And now clearly this is going to be negative 0.004s. And this is the integral of 1 over v, which is the natural log of v calculated at 10 and 80. So it is going to be natural log of 10 minus natural log of 80. And if you solve for s or delta s in this case, because again I assume that initial position is 0, or it doesn't matter, you can just call them s1 and s2, and the difference between them is delta s. So not going to change anything. If I do that, then I'm going to find that it takes about 520 meters for it to go to that smaller speed. Okay, so this number here is going to be 520 meters. So one way to solve this problem was to skip velocity at all versus time and go to time independent equation. That gives you this one. Now, is there another way to do it? Yes. The other way to do this is here, when we solve for the time, this is another way to do this problem. So remember here that we came down to dv over negative v squared is 0.004 t, right? So I come here and I write it again. This is what we had. Now, the initial velocity is 80, right? And this time is the initial time when it lands, it hits, so 0. Then instead of using constant numbers for the upper limits, I use arbitrary parameters. So I use t, arbitrary t, and here I use what? Arbitrary v of t. if I do that, then I'm going to get 1 over v of t minus 1 over 80 is equal to 0.004 t. And guess what? This one is giving us, yes, v as a function of time. So if I solve for v of t here, I take this 180 over the other side, take a common denominator, and then take reciprocal of both sides. Then you would get, so if I bring this over here, take a common denominator, right? Then take reciprocal, it's going to be 80 over 1 plus 0.32t. So you can find velocity as a function of time if you want, and then if you want, you can integrate this. You can say delta S now is the integral of Vt dt from initial time to the final time, and final time was 21.9 seconds. And for v of t, you're going to plug in this function. So it is going to be integral from 0 to 21.9 of 80 dt over 1 plus 0.32 t. So you have to calculate this integral. And I bet you can. All you need to do is to call this whole thing u, right? And if 80 comes out of the integral, then du from here, you see du is what? If that's u, then du is 0.32 dt, but this is 1 times dt. So what I do, I multiply it by a 0.32 and I divide it by a 0.32. So it is going to be 80, which came out, divided by this 0.32, the integral of 0.32 dt over 1 plus 0.32 t. Okay? And now this guy is du, and this one is u. And integral of du over u is what? Natural log of u. So it is going to be 80 over 0.32, natural log of u. But u itself is 1 plus what? 0.32 t. And then for t, you plug in the upper and lower numbers, which is 0 and 21.9. So you end up with 80 divided by 0.32 times natural log of 1 plus 0.32 times 21.9 minus natural log of simply 1. Which again, if you do it, you're going to get the 520 meters. Okay, but you see clearly if I skip the time and finding v as a function of time and directly going between a, v, and s by time independent equation, finding displacement is much easier. Okay, so this is the first problem that we solved.